The universe is alive, not in the way we think of life, but in its endless, rhythmic pulse. It expands, stretching galaxies farther apart like dots on an inflating balloon. Then some theories suggest it might one day reverse, collapsing back in on itself in a cosmic sigh. This isn't poetry, it's the reality of existence, written in the fabric of space and time. For centuries, humans have looked up at the night sky and wondered, is the universe eternal, or does it have a beginning and an end? Today, we stand on the shoulders of giants Einstein, Hubble, Hawking, and peer deeper than ever into these questions. The answers we're finding are stranger than fiction, painting a picture of a cosmos that's anything but static. Think about this. Every second, the space between galaxies grows wider, not because they're moving through space, but because space itself is stretching. It's as if the ground beneath your feet kept spreading apart whether you walked or stood still. This isn't just a curious observation, it's the heartbeat of the universe, the engine driving its evolution. But here's the mind-bending part. What if this expansion isn't forever? Some theories suggest that gravity, the very force that holds planets and stars together, could one day overpower this expansion, pulling everything back into a single, unimaginably dense point, a big crunch, the mirror image of the Big Bang. The universe might not just breathe, it could be trapped in an endless cycle of inhales and exhales. What does this mean for us, for the atoms that make up our bodies, for the light from distant stars that's taken billions of years to reach our eyes? This video is a journey into the unknown, where we'll unravel the most profound theories on cosmic expansion and contraction. We'll explore how dark energy might be pushing the universe apart, how quantum fluctuations could hint at a multiverse, and whether time itself could reset in a cosmic rebound. These aren't just abstract ideas, they're the keys to understanding our place in the grand scheme of things. So buckle up. By the end, you won't just see the night sky the same way again. You'll feel it, the vast, breathing cosmos, and your tiny, extraordinary part in its story. The Big Bang wasn't an explosion in space, it was the explosion of space itself. Picture this, all the energy, matter, and even time we know, squeezed into a point smaller than an atom, hotter than the core of any star. Then, in an instant, it unfurled like a cosmic firework, stretching the very fabric of reality. That moment, 13.8 billion years ago, didn't just create the universe, it defined the rules it would follow forever. But how do we know this actually happened? The clues are everywhere, written in the oldest light we can see, the cosmic microwave background. This faint glow, discovered by accident in the 1960s, is the afterimage of the Big Bang's first light, cooled over eons into microwaves that still echo across the cosmos. Then there's the redshift of distant galaxies, the telltale sign that the universe is still stretching. When astronomers like Edwin Hubble noticed that galaxies were moving away from us, and the farther they were, the faster they raced, it was proof that space itself was growing, carrying galaxies along like driftwood on a rising tide. But here's where it gets even stranger. The Big Bang wasn't just an event in the past, it's happening right now. Every new inch of space that forms between galaxies is part of that same expansion, a living reminder that the universe is still unfolding. So what sparked it all? Why did that infinitesimally small, unimaginably hot point decide to burst into existence? That's where the mysteries deepen. Some theories suggest quantum fluctuations, tiny ripples in the fabric of nothingness, could have tipped the scales, transforming emptiness into everything. Others propose that our universe is just one bubble in an endless froth of multiverses, each with its own unique physics. But one thing's certain, the Big Bang didn't just set the stage for stars and planets. It coded the universe's fate into its first moments, determining whether it would expand forever, collapse back in on itself, or find some other, even stranger destiny. And that's the real power of this theory. It's not just about where we came from, but where we're headed. Dark energy is the universe's best-kept secret, an invisible hand stretching the cosmos faster than anyone expected. When astronomers first noticed distant supernovas shining dimmer than they should have been, it wasn't a mistake in their calculations. It was evidence that the universe wasn't just expanding, it was accelerating, as if some unseen force was pressing down on the cosmic gas pedal. This discovery flipped cosmology upside down. For centuries, we assumed gravity would eventually slow the universe's expansion, like a ball tossed upward, gradually losing speed. But dark energy does the opposite. Imagine throwing that ball and watching it shoot faster into the sky, defying gravity with every second. That's the puzzle scientists face. What could possibly overpower gravity on such a colossal scale? One leading idea is Einstein's cosmological constant, a sort of energy woven into the fabric of space itself. Think of empty space not as true emptiness, but as a bubbling quantum foam where particles flicker in and out of existence. These fleeting bursts might generate a repulsive force pushing galaxies apart. Then there's quintessence, a more exotic possibility. Unlike the steady hum of the cosmological constant, quintessence could be a dynamic field, shifting over time like an invisible tide. Some theories even suggest it might grow stronger, eventually ripping atoms apart in a Big Rip scenario, a cosmic unraveling so violent it would make the Big Bang look gentle. But here's the twist: dark energy might not be a force at all. It could be a sign that Einstein's theory of gravity is incomplete, that on the largest scales, gravity behaves in ways we don't yet understand. The stakes couldn't be higher. If dark energy keeps accelerating, galaxies beyond our local group will someday vanish over the cosmic horizon, their light stretched beyond detection. The universe could become a lonely, scattered place. Yet for all its mystery, dark energy isn't just a cosmic villain, it's also the reason we exist. Without it, the universe might have collapsed long before stars or planets could form. So while it challenges everything we know, it also holds the key to understanding our most profound question: what is the universe meant to become? The Big Crunch is the universe's ultimate callback, a theory that turns the cosmic story into a loop rather than a one-way trip. Imagine if every galaxy racing away from us today suddenly hit the brakes, reversed course, and began hurtling back toward a shared fate. That's the essence of this hypothesis. Gravity, the silent sculptor of the cosmos, could one day triumph over dark energy's relentless push. Instead of expanding forever, the universe might collapse in on itself like a deflating balloon until every star, planet, and atom is crushed back into a singularity. But how plausible is this dramatic reversal? For decades, the Big Crunch was the leading contender for the universe's final act. After all, gravity never sleeps. It's the force that binds your feet to the ground and keeps planets orbiting stars. If there's enough matter in the cosmos, its collective pull could slow expansion to a halt, then drag everything inward. Picture a pendulum swinging out into space, pausing at its peak, then falling back toward the center. The math once suggested this was inevitable. Then came dark energy's plot twist, the discovery that the universe's expansion is accelerating, not slowing, threw the Big Crunch into doubt. Suddenly, the pendulum wasn't just failing to swing back, it was being yanked harder outward. Yet some physicists aren't ready to dismiss the idea entirely. They proposed dark energy might weaken over time, or that unknown forces could emerge to counterbalance it. There's even a wildcard scenario where the universe's expansion slows just enough for gravity to gain the upper hand billions of years from now, long after the last stars have burned out. But here's the real kicker: if the Big Crunch happens, it might not be the end. Some models suggest the collapse could reach such extreme densities that it triggers another Big Bang, a cosmic reset button. In this cyclical universe, every ending births a new beginning, like a phoenix rising from its own ashes. Time itself could fold back in ways we can't comprehend, erasing all traces of the previous cycle while setting the stage for a fresh cosmos. So what would a big crunch look like? Picture the sky growing hotter as galaxies merge into a fiery glow. Stars would vanish faster than they formed, compressed into oblivion. In the final moments, even atoms would shatter under the pressure, unraveling the very fabric of reality. But whether this leads to eternal silence or a rebirth is one of the greatest mysteries in physics. It forces us to ask, is the universe a single, unfolding drama or an endless play with infinite acts? The answer might lie in the delicate tug of war between two invisible giants, dark energy and gravity, locked in a battle for cosmic supremacy. Cosmic inflation rewrote the rulebook for how we understand the universe's first moments. Instead of a steady expansion from the Big Bang, picture this: a speck of space smaller than a proton suddenly ballooning to the size of a grapefruit in less than a trillionth of a second. That's not just fast, it's faster than the speed of light itself, defying everything we thought we knew about physics. Alan Guth proposed this radical idea in the 1980s to solve a cosmic mystery. Why does the universe look so eerily similar in all directions? Without inflation, regions of space too far apart to ever communicate would somehow share identical temperatures and densities, like strangers on opposite sides of the world wearing the same outfit by pure coincidence. The secret lies in something called the inflation field, a kind of cosmic fuel that powered this runaway expansion. Think of it like a snowball rolling down an endless hill, gathering energy until it transforms into an avalanche. As this field decayed, its pent-up energy flooded the universe, heating it into the seething plasma of particles we recognize as the Big Bang's aftermath. But here's where it gets wild. Tiny quantum fluctuations in that field didn't just vanish. They were stretched across the cosmos, becoming the seeds for everything we see today. Those microscopic ripples, they're the reason galaxies exist, the reason you exist. Without them, the universe would have been a featureless sea of uniformity. Could inflation happen again? Some theories suggest our universe might be just one bubble in a frothing multiverse, where new patches of space constantly inflate into their own cosmic realms, each with different laws of physics. It's like a boiling pot of water where every bubble is a brand new universe forever out of reach. Others speculate that inflation might not be a one-time event, that hidden triggers in the fabric of reality could launch another exponential expansion, rewriting the cosmos all over again. The implications are staggering. If inflation is true, it means the universe we can observe is just a vanishingly small fraction of everything that exists. The real cosmos could be unimaginably vaster, with regions so distant their light will never reach us. But inflation isn't just about scale, it's about destiny. The way space stretched in those first moments determined whether galaxies could form, whether life could emerge, and whether the universe would ever have a chance to contemplate itself. So while we'll never see beyond our cosmic horizon, inflation theory gives us something even more precious, a glimpse into the forces that set the stage for existence itself. What if our universe isn't alone? What if it's just one page in an infinite cosmic library, where every book tells a different story of reality? This is the multiverse hypothesis, a theory so vast it reshapes how we define existence itself. Picture inflation, the universe's explosive initial growth, not as a one-time event, but as a perpetual engine, endlessly birthing new universes like bubbles in a boiling pot. Each bubble inflates into its own isolated realm with unique physics, some where gravity is stronger, others where time flows backward, or where matter never clumped into stars at all. The idea didn't spring from science fiction. It's a natural extension of inflation theory, where quantum fluctuations could spawn pockets of space so distinct they might as well be separate realities. Imagine tossing a handful of dice. Every possible outcome lands somewhere, creating universes where every conceivable law of physics plays out. In one, atoms might never form. In another, life could thrive under conditions we'd find impossible. The chilling beauty, we'll likely never see these other universes. Their light can't reach us across the unimaginable gulfs between bubbles, leaving them forever hidden. Yet scientists haven't given up on clues. Some hunt for bruises in our cosmos, anomalies in the cosmic microwave background where our bubble universe might have collided with another. Others explore string theory's landscape, where mathematical solutions suggest a staggering 10 to the 500 possible universes, each with its own rules. Philosophers, meanwhile, wrestle with the implications. If infinite versions of reality exist, does that make our laws of physics arbitrary? Is there a typical universe, or are we just lucky winners in a cosmic lottery where most realities are barren? The multiverse forces us to confront humbling questions about our place in existence. If every possible outcome happens somewhere, does choice lose meaning? Or does it mean that somewhere, every path we didn't take is playing out in another universe? This isn't just speculative science, it's a mirror held up to our deepest curiosities. Whether the multiverse is real or not, the very possibility stretches our imagination to its limits, revealing how much we have yet to learn about the nature of everything. String theory whispers a tantalizing possibility that the fundamental building blocks of reality aren't particles at all, but tiny, vibrating strands of energy, each dancing to its own cosmic rhythm. Imagine plucking a guitar string and hearing not just one note, but every possible frequency of the universe. That's the essence of this revolutionary idea. Every particle, every force, even space and time itself, could arise from the harmonies of these microscopic strings. But what does this have to do with cosmic expansion? The answer might lie in dimensions we can't see. While our everyday experience is limited to 3 dimensions of space and 1 of time, string theory demands at least 10, maybe more. The extra dimensions aren't just theoretical clutter. They could be curled up so tightly that even atoms seem vast by comparison, a process called compactification. Picture a garden hose. From a distance, it looks like a simple line, but up close, you see it's actually a cylinder. Those hidden dimensions might hold the key to gravity's puzzling weakness compared to other forces, or even dark energy's mysterious push. Then there are branes, short for membranes, massive structures floating in higher dimensional space. Our entire universe could be a 3-dimensional brane, like a sheet of paper suspended in a vast, unseen realm. If another brane floated nearby, its gravity might leak into ours, subtly altering how galaxies move. Some theories even suggest the Big Bang itself could have been a collision between branes, a cosmic crash that set our universe into motion. But here's the wildest twist. String theory doesn't just offer one explanation for cosmic expansion, it offers countless. The landscape of possible solutions includes universes that expand forever, others that collapse, and some that oscillate between the two. It's as if the laws of physics are a piano with infinite keys, and our universe is just one melody among an endless symphony of possibilities. Critics argue that string theory's lack of experimental proof makes it more philosophy than science. Yet its mathematical beauty keeps drawing researchers back. If proven true, it wouldn't just explain the universe's expansion, it would rewrite our understanding of reality itself, revealing a cosmos far stranger and more interconnected than we ever dreamed. So while the strings remain silent for now, their potential song hints at a harmony we're only beginning to hear. The cyclic model dares to ask a question that feels almost mythical. What if the universe has no true beginning or end, just an infinite rhythm of rebirth? Unlike the one-way journey of the Big Bang, this theory paints the cosmos as a phoenix perpetually rising from its own ashes. At its heart are branes, those elusive, higher-dimensional sheets of reality that could collide like symbols in the dark, each crash igniting a new cycle of expansion. Paul Steinhardt and Neil Turok's vision isn't just poetic. It's a radical reimagining of time itself, where the Big Bang wasn't a singular event, but the latest in an endless series. Picture two parallel worlds drifting through a hidden dimension, drawn together by forces we can't see. When they meet, their collision unleashes enough energy to forge an entire universe's worth of matter and radiation, but without the incomprehensible singularity of traditional Big Bang cosmology. It's a gentler genesis, one that sidesteps the need for a starting point by making creation a recurring phenomenon. This could explain why the universe appears so finely tuned for life. If cycles have repeated countless times, each one naturally selects for conditions that allow galaxies, stars, and planets to form. But does this solve more puzzles than it creates? The cyclic model elegantly dodges the thorny question of what came before the Big Bang, because in this framework there's no before. Time loops back on itself like a Möbius strip. It also offers a fresh take on dark energy. Instead of a mysterious force stretching space apart forever, dark energy might be the very agent that prepares the universe for its next collision, smoothing and flattening space until branes are destined to meet again. Critics, though, point to gaps. The model requires extra dimensions and finely tuned brane dynamics elements we can't yet observe. And while it avoids a singularity, the collisions themselves would generate universe-scorching heat, raising questions about how complex structures like galaxies survive cycle after cycle. Yet the boldness of the idea captivates. If true, the cosmic microwave background might hide faint echoes of previous cycles, like scars from ancient crashes. Comparing it to inflation theory reveals a stark philosophical divide. Inflation suggests a single, volatile beginning, while the cyclic model offers eternity. One paints the universe as a lone bubble in an endless foam, the other as a heartbeat in an immortal body. Both compel us to rethink not just where we came from, but what time really means. Whether the cycles are real or not, they remind us that the universe's story might be far grander and stranger than we ever imagined. Dark matter is the universe's silent architect, an invisible hand sculpting galaxies and guiding the cosmic dance of expansion itself. While dark energy stretches space apart, dark matter works in opposition, its gravitational pull acting like cosmic glue, holding everything together. Think of it this way: if the universe were a vast ocean, dark energy would be the tide carrying ships outward, while dark matter is the unseen current keeping them from drifting into oblivion. Without it, galaxies would fly apart, their stars scattered like leaves in a storm. Yet despite making up roughly 85% of all matter in the cosmos, dark matter refuses to reveal itself directly. It doesn't emit light, absorb light, or interact with electromagnetic forces at all. We only know it's there because of its gravitational fingerprints, the way galaxies spin faster than they should, or how light bends around seemingly empty patches of space. So what could this mysterious substance be? One leading candidate is WIMP, weakly interacting massive particles. These hypothetical particles are thought to be heavy, slow-moving, and nearly ghost-like, passing through ordinary matter as if it weren't there. Imagine standing in a blizzard where every snowflake is a WIMP. You'd feel no impact even as trillions stream through you every second, yet their collective gravity could be enough to shape the cosmos. Another possibility is action's ultra-light particles that might behave more like a pervasive quantum fog, filling space with an imperceptible ripple. Then there's the wild card: what if dark matter isn't a single entity at all? Some theories suggest it could be a mix of particles or even primordial black holes, those ancient remnants from the universe's earliest moments. The stakes couldn't be higher. If dark matter interacts with itself in ways we haven't detected, perhaps through some hidden force, it could reshape our understanding of gravity itself. Experiments deep underground in abandoned mines and mountain tunnels are hunting for these elusive particles shielded from cosmic interference. Others scan the skies for faint distortions in starlight or the telltale glow of colliding dark matter clouds. But here's the twist. Dark matter isn't just about the past or present, it's about the universe's ultimate fate. If dark energy's push continues to accelerate, dark matter might be the last force resisting total cosmic dissolution. Or if dark matter's grip weakens over time, galaxies could unravel faster than we ever imagined. The interplay between these two invisible giants, dark matter's pull and dark energy's push, will decide whether the universe ends in fire, ice, or something stranger still. And that's the real magic of this mystery. It's not just about what dark matter is, but what it means for the story we're all a part of, written in the invisible ink of gravity itself. At the very beginning, when the universe was smaller than a single atom, it wasn't a smooth, featureless void. It was a seething ocean of quantum uncertainty. Tiny fluctuations rippled through this primordial energy, random blips where particles flickered in and out of existence, governed by the strange rules of quantum mechanics. These fluctuations were unimaginably small, less than a trillionth of the size of a proton, but they held the blueprint for everything that would come. The expansion of the universe didn't erase these microscopic wrinkles. Instead, it stretched them, magnifying them into the vast cosmic web of galaxies and voids we see today. How does randomness on such an infinitesimal scale transform into the grand structure of the cosmos? Picture throwing a handful of pebbles into a still pond. The ripples spread outward, interacting with each other, creating patterns of crests and troughs. Now imagine that pond is the fabric of space itself, and instead of water, it's filled with energy that would eventually cool into matter. Those initial ripples, born from quantum uncertainty, became the seeds for matter to clump together, pulled by gravity into dense knots where galaxies would one day form. Cosmic inflation played a crucial role here. That brief, explosive expansion didn't just stretch space, it stretched the quantum fluctuations along with it, locking them in place like a photograph of the universe's earliest moments. Without inflation, those tiny variations would have remained insignificant, lost in the noise, but inflation amplified them, turning subatomic ripples into continent-sized differences in density. As the universe cooled and matter began to coalesce, gravity took over, pulling more matter toward these denser regions. Over billions of years, these slight overdensities grew into galaxies, galaxy clusters, and the sprawling filaments of the cosmic web. What's astonishing is that we can still see these ancient fingerprints today. The cosmic microwave background, the afterglow of the Big Bang, shows slight temperature variations, hotter and colder patches that correspond to those early density fluctuations. These aren't just relics of the past, they're the reason you exist. If the fluctuations had been any weaker, matter might never have clumped together enough to form stars. Any stronger, and the universe might have collapsed back into black holes before life could emerge. This raises a profound question. Were these fluctuations truly random, or was there some deeper mechanism at work? Some theories suggest that quantum processes during inflation could have been influenced by even earlier conditions, perhaps traces of a pre-inflationary universe or interactions with other dimensions. Others propose that what we perceive as randomness might actually be the signature of a more fundamental order hidden beneath the quantum veil. Either way, the story of quantum fluctuations is the story of cosmic destiny written in the smallest possible script. Every galaxy, every star, every planet owes its existence to those fleeting irregularities in the infant universe. It's a humbling thought. The vast structures we see when we look up at the night sky began as whispers in the quantum dark, stretched across time and space by the unrelenting expansion of the cosmos. And somewhere in that grand design, a particular set of fluctuations led to a tiny blue planet where atoms could arrange themselves just right to wonder about it all. The holographic principle turns our intuition about reality inside out. What if the three-dimensional universe we perceive is nothing more than a shadow, a projection from information encoded on a distant two-dimensional surface? This idea, born from the study of black holes, suggests that everything we see, galaxies, stars, even our own thoughts, might be like a movie playing on the cosmic equivalent of a flat screen. It sounds like science fiction, but the mathematics behind it is surprisingly robust, rooted in the way black holes preserve information at their boundaries. Imagine a black hole's event horizon, the point of no return where gravity's grip becomes irreversible. In the 1970s, physicist Jacob Bekenstein calculated that the entropy, or disorder, of a black hole isn't proportional to its volume but to the area of its horizon. Later, Stephen Hawking showed that black holes emit radiation, slowly evaporating over unimaginable timescales. This raised a paradox. If a black hole vanishes, what happens to all the matter and energy it swallowed? The answer, according to the holographic principle, is that the information isn't lost, it's smeared across the horizon like data etched onto a cosmic hard drive. Now take this bizarre insight and scale it up to the entire universe. If a black hole's interior can be described entirely by information on its surface, why couldn't the same be true for reality as a whole? Some theorists propose that our universe might be a hologram, its three-dimensional richness an illusion generated by quantum bits living on a distant two-dimensional boundary. In this view, every particle interaction, every ripple of gravity, every moment of time is just a decoded message from that faraway surface. What does this mean for cosmic expansion? If the universe is a hologram, then the stretching of space we observe might not be fundamental. It could be a side effect of how the underlying information is processed. Think of it like zooming in on a digital image. The pixels don't change, but the way they're displayed creates the illusion of depth and motion. Similarly, the expansion of the universe might not involve space itself growing, but rather the way information on that boundary surface is translated into our experience. This raises staggering implications for the nature of reality. If the holographic principle is correct, then time and space aren't the bedrock of existence, they're emergent phenomena, secondary to the flow of information. It's as if the universe is a vast, interconnected computation, with the laws of physics acting like software running on hidden hardware. Some versions of the theory even suggest that the boundary encoding our reality could lie in the far future, meaning the entire history of the cosmos is pre-written, unfolding like a cosmic film reel. Critics argue that the holographic principle, while mathematically elegant, remains untested. How could we ever detect a two-dimensional boundary we can't see or interact with? Yet there are tantalizing hints. Some physicists hunt for subtle noise in gravitational wave detectors, a potential signature of the universe's pixelated nature. Others look for anomalies in high-energy particle collisions that might betray an underlying granularity to spacetime. Whether the holographic principle holds up or not, it forces us to confront a profound question. Is reality as we experience it the whole story, or just the surface of something far deeper? If the universe is indeed a hologram, then every galaxy, every atom, every thought is part of an intricate dance of information, a dance we're only beginning to decipher. And that realization doesn't just change how we see the cosmos. It changes how we see ourselves, not as passive observers, but as participants in a reality far stranger and more interconnected than we ever imagined. The universe doesn't end with a bang or a crunch, but with a whisper. Heat death is the slow fade of all energy, the final sigh of a cosmos that's exhausted every possible spark of activity. Picture a future so distant it makes the age of our universe seem like a single heartbeat. stars, having burned through their fuel, vanish into darkness. Galaxies, stretched beyond recognition by relentless expansion, dissolve into isolated islands of dying matter. Even black holes, those cosmic vaults once thought to be eternal, evaporate over eons, leaking radiation until they too disappear. What's left is a vast, featureless void where temperature differences no longer exist, where nothing happens not just for years but forever. It's the ultimate triumph of entropy, the universe settling into a state of perfect, unchanging equilibrium. But how do we know this is our fate? The clues lie in thermodynamics, the same laws that govern steam engines and ice melting in sunlight. Energy always flows from hot to cold, from ordered to disordered, and the cosmos is no exception. Dark energy's accelerating push ensures that matter spreads so thin that particles can't collide to create new structures. Eventually, even protons, the building blocks of atoms, might decay, unraveling the last remnants of solid matter. The cosmic microwave background, now a faint whisper of warmth, would cool to undetectable levels, leaving no trace that the universe was ever anything but a silent, infinite dark. Yet some scientists refuse to accept this icy finale as inevitable. What if dark energy isn't constant? If it weakens over time, gravity might regain dominance, pulling the universe back from the brink. Or perhaps new, undiscovered forces could emerge, rewriting the rules of thermodynamics in ways we can't yet imagine. String theory's hidden dimensions or quantum gravity's paradoxes might hold the key to a different destiny, one where heat death isn't the last word. Then there's the wild card of vacuum decay. If our universe exists in a false vacuum, a metastable state that could collapse into a lower energy configuration, a single quantum event might trigger a catastrophic phase transition. A bubble of true vacuum could expand at light speed, rewriting the laws of physics in its wake and erasing everything we know. It sounds apocalyptic, but paradoxically, it could also reset the cosmic clock, birthing a new universe with different constants and possibilities. The chilling beauty of heat death isn't just its inevitability, but what it teaches us about time. If the universe reaches absolute equilibrium with no energy gradients left to drive change, does time itself lose meaning? Without events to mark its passage, time might cease to exist as anything but an abstract concept, a frozen clock face with no hands left to move. So while heat death paints the bleakest possible future, it also underscores how extraordinary our present moment is. We exist in a sliver of cosmic time when stars still shine, when galaxies still spin, when questions can still be asked. The universe may one day forget itself, but for now, it's alive with possibility, and that makes every second of its story worth witnessing. The Big Rip isn't just an end to the universe, it's an unraveling, a moment when the fabric of reality itself is stretched too thin to hold together. Picture dark energy not just nudging galaxies apart, but growing stronger over time, its grip tightening until no force in the cosmos can resist it. First, galaxy clusters would be ripped from one another. Then individual galaxies would disintegrate as stars lose their gravitational tether. But the horror doesn't stop there. In the final hours, planets would be torn from their orbits, and stars themselves would burst apart as space expands faster than light can travel. Even atoms, the building blocks of everything we know, would be shredded into their fundamental particles as the space between them grows faster than the forces holding them together. The universe wouldn't just fade into darkness, it would dissolve into chaos. How soon could this happen? The answer depends on dark energy's true nature. If it behaves like Einstein's cosmological constant, unchanging and steady, the Big Rip might never occur. But if it's a more sinister force, something like quintessence, which grows stronger over time, the countdown could already be ticking. Current estimates suggest a worst-case scenario of around 22 billion years from now, long after the last stars have burned out. That might sound comforting, but on cosmic timescales, it's a blink of an eye. Critics of the Big Rip point to gaps in our understanding. Why would dark energy suddenly strengthen after billions of years of stability? Could quantum effects or undiscovered physics intervene before the cataclysm? Some theorists argue that the universe might find an equilibrium, or that new forces could emerge to counterbalance dark energy's destructive potential. Others propose that the Big Rip might not be the end at all, that the extreme conditions could trigger a rebound, birthing a new universe from the wreckage of the old. What's certain is that the Big Rip forces us to confront the fragility of existence. If space itself can be torn apart, then the laws of physics as we know them aren't just guidelines, they're temporary, vulnerable to forces beyond our control. It's a humbling reminder that the universe, for all its majesty, might not be permanent. And yet, even in this apocalyptic vision, there's a strange beauty. The cosmos, in its final act, would reveal the raw power of the forces that shaped it from the beginning. Whether the Big Rip is our fate or just a speculative nightmare, it compels us to ask how much of reality is truly set in stone and how much hangs by a thread. Brane cosmology flips our understanding of the universe on its head, literally. Imagine reality isn't the vast three-dimensional expanse we perceive, but a thin, shimmering membrane adrift in a hidden dimension, like a sheet of paper floating in a pitch-black room. This radical idea, born from the marriage of string theory and cosmology, suggests our entire cosmos might be just one of many branes' higher dimensional surfaces bumping and weaving through a space we can't see. And here's the kicker: these collisions could be the cosmic engines behind everything from the Big Bang to the universe's accelerating expansion. Take the Ecporotic model, for instance. Picture two parallel branes separated by an infinitesimal gap in an unseen dimension. Over eons, they drift closer, drawn together by an invisible force until, bang, they collide. The energy of that impact doesn't just create heat and light. It births an entire universe, flooding our brain with matter and radiation. Unlike the singularity of traditional Big Bang theory, this collision is smooth, almost elegant, offering a way to explain the universe's startling uniformity without invoking inflation's breakneck expansion. The cosmic microwave background's near-perfect symmetry, that's just the afterglow of two branes kissing in the dark. But branes don't just explain beginnings, they might hold the key to dark energy. If our universe is a brane embedded in a higher dimensional bulk, gravity could be leaking into it from neighboring branes, acting as an invisible push or pull on cosmic scales. Think of it like a ship's sail billowing in a wind we can't feel. Some models even suggest that what we perceive as dark energy's relentless expansion could be the slow warping of our brain, stretching like taut fabric under tension from unseen forces. The implications are staggering. If branes exist, our universe isn't just one story. It's a single page in a library of realities, each with its own physics, its own stars, its own potential for life. Some might hover millimeters away in a higher dimension, forever out of reach. Others could have collided with ours long ago, leaving faint echoes in the cosmic microwave background, like cosmic fingerprints on a celestial crime scene. Yet for all its elegance, brane cosmology isn't without challenges. How do we test a theory that hinges on dimensions we can't access? Some physicists hunt for gravitational waves left over from ancient brane collisions, while others scour particle accelerators for signs of extra-dimensional leakage. The math is beautiful, but until evidence emerges, these ideas remain tantalizing possibilities, a reminder that the universe's greatest mysteries might not lie in the stars, but in the spaces between dimensions we've yet to imagine. The Anthropic principle cuts to the heart of one of cosmology's most haunting questions. Why does the universe seem custom-built for life? Consider the delicate balance of cosmic constants. If gravity were slightly stronger, stars would burn out in a blink. If the electromagnetic force were weaker, atoms could never bond. The expansion rate of the universe is just as precise. Too fast and matter would scatter before galaxies formed. Too slow and everything would collapse back into a black hole. It's as if countless dials were set to perfect values, all conspiring to make our existence possible. But does this fine-tuning demand an explanation, or is it simply a quirk of our perspective? Proponents of the anthropic principle argue it's the latter. We observe these precise conditions because we're here to observe them. In other words, a universe with different parameters might exist, but it would lack conscious beings to ponder its laws. It's like a fish marveling at how perfectly water suits its gills, unaware of the vast deserts where life couldn't thrive. This idea takes a dramatic turn with the multiverse hypothesis. If infinite universes bubble into existence, each with random physical constants, then statistically, some must hit the cosmic jackpot conditions just right for life. We're not special, we're just the lucky winners in a lottery with near zero odds. Critics, though, argue this pushes the problem back a step. What creates these universes and why do they vary? Others propose more radical answers. Perhaps the constants aren't arbitrary at all, but emerge from deeper, undiscovered laws that make life inevitable. Philosophically, the anthropic principle walks a tightrope between humility and hubris. It reminds us that our universe might be one of many, yet also suggests that consciousness plays an unexpected role in shaping reality. Some interpretations even flirt with the idea of a participatory universe, where observation itself influences cosmic structure, a notion that blurs the line between physics and metaphysics. Whether the anthropic principle is a profound insight or a cosmic shrug, it forces us to confront the strangeness of our place in existence. The universe's expansion, its constants, its very fabric might feel inevitable to us, but only because we're here to witness them. And that realization doesn't just reshape how we see the cosmos, it redefines what it means to ask why in the first place. Loop quantum gravity offers a radical reimagining of space-time itself, not as a smooth, continuous fabric, but as a shimmering tapestry of interwoven loops, each smaller than the smallest particle. Unlike string theory's vibrating strands, these loops don't float in space, they are space. Picture the universe as a cosmic mesh, where every intersection hums with quantum energy, and the gaps between them define the very notion of distance. This isn't just abstract math, it's a framework that could rewrite our understanding of cosmic expansion from the ground up. At the heart of this theory lies the idea that space-time is granular, like pixels on a screen. These quantum loops resist being squeezed beyond a certain point, meaning the Big Bang might not have been a singularity, an infinitely dense point, but a rebound from a previous collapse. Imagine squeezing a spring. The harder you press, the stronger it pushes back. In loop quantum cosmology, the universe could have bounced from a prior contraction, avoiding the infinite densities that break Einstein's equations. This paints the Big Bang not as a beginning, but as a turning point in an endless cycle where expansion follows contraction like the tides. What does this mean for dark energy and the universe's accelerating expansion? Here, loop quantum gravity takes a surprising turn. The theory suggests that at extremely small scales, the geometry of space-time could behave like a fluid with properties that mimic repulsive gravity, an effect not unlike dark energy's push. It's as if the quantum structure of space itself holds a memory of its past, leaving faint imprints on how the cosmos expands today. Critics argue these predictions are hard to test, but proponents point to subtle signatures in the cosmic microwave background or gravitational waves that might one day reveal space's granular nature. The real bombshell, loop quantum gravity could banish singularities entirely. Black holes wouldn't end in infinitely dense points but transition into white holes, spewing out matter like a cosmic geyser. Even time might emerge from the spin of these quantum loops, meaning the arrow of time. The reason we remember the past but not the future could be woven into the universe's very architecture. Comparing this to mainstream cosmology reveals a philosophical clash. Inflation and dark energy rely on smooth, classical space-time, while loop quantum gravity insists the fabric of reality is fundamentally choppy. Yet both grapple with the same mystery. Why does the universe expand the way it does? Whether space is a quantum tapestry or a stretching elastic sheet, the answer might lie in the cracks between our current theories, waiting for the next leap in our cosmic understanding. Entropy isn't just a scientific concept, it's the silent architect of cosmic fate, shaping everything from the birth of stars to the universe's dying breath. At its core, entropy is the universe's way of keeping score, a relentless push toward disorder that dictates why time only flows forward, why coffee cools but never spontaneously reheats, and why the cosmos might one day reach a state of perfect, lifeless equilibrium. But here's the twist: entropy isn't just a force of decay. It's the engine behind some of the universe's most profound transformations, including its expansion and potential collapse. Take black holes, the universe's ultimate entropy factories. When matter falls into a black hole, it doesn't just vanish. It leaves a permanent mark on the cosmos in the form of entropy, encoded on the black hole's event horizon like cosmic graffiti. Stephen Hawking's groundbreaking work revealed that black holes emit radiation, slowly evaporating over eons. But as they fade, they don't just disappear. They leave behind a legacy of scrambled information, a puzzle that hints at entropy's deep connection to space-time itself. This discovery upended our understanding of thermodynamics, showing that even the darkest corners of the universe play by entropy's rules. Now zoom out to the cosmic scale. The universe's expansion isn't just a matter of galaxies drifting apart. It's a theater where entropy takes center stage. As space stretches, the energy within it becomes more diluted, like ink dissolving in an ever-growing pool of water. This means the universe isn't just getting bigger, it's settling into a state of higher entropy where energy is evenly spread and nothing can happen: no stars, no life, just a featureless void. This is the heat-death scenario, the ultimate victory of disorder over structure. But could entropy also hold the key to cosmic rebirth? Some theories suggest that if the universe collapses in a big crunch, the unimaginable heat and density of that moment might reset entropy, winding the cosmic clock back to zero. It's like shaking a snow globe. All the swirling flakes settle into a new configuration, potentially allowing for another cycle of creation. Others argue that entropy's grip is too strong, that even a collapsing universe would only deepen its disorder, leaving no room for a fresh start. The arrow of time adds another layer to this mystery. Why do we remember the past but not the future? Entropy provides the answer. Time's one-way street is paved with increasing disorder. Every moment, from a shattered glass to a dying star, is a step toward higher entropy. But what if the universe's expansion could bend this arrow? In regions of extreme curvature or near black holes, some models hint that entropy might behave unpredictably, blurring the line between past and future. Ultimately, entropy isn't just a footnote in the cosmic story, it's the plot itself. Whether the universe expands forever or collapses in on itself, whether time is an unbreakable arrow or a flexible ribbon, entropy will have the final word. And that leaves us with a haunting question. If disorder always wins, does that make the universe's fleeting moments of structure, galaxies, planets, life, even more miraculous? The answer lies in the delicate dance between chaos and order, a dance that began with the Big Bang and will echo until the last star burns out. Vacuum decay is the universe's ultimate reset button, a phenomenon so destructive it could erase reality as we know it, not with a bang, but with a quiet, unstoppable rewrite of physics itself. Picture the universe as a valley nestled between mountains, where the ground beneath our feet represents the stable, predictable laws we rely on: gravity, electromagnetism, the speed of light. But what if that valley isn't the lowest point? What if just beyond these mountains lies a deeper chasm, a truer state of vacuum where energy is lower and the laws are unrecognizable. This is the spine-chilling premise of false vacuum theory. Our universe might be teetering on a precarious ledge, and one quantum nudge could send it tumbling into the abyss. The science behind this nightmare scenario hinges on quantum fields, the invisible scaffolding that underpins reality. These fields permeate every inch of space, dictating how particles behave and forces interact. Most of the time, they sit in their lowest energy states like marbles resting at the bottom of a bowl. But if our current vacuum is only false, it's more like a marble balanced on a plateau, stable for now but capable of rolling catastrophically downhill given the right perturbation. Quantum fluctuations, those tiny blips of uncertainty at the subatomic level, could provide that nudge. If one occurs in just the right way, it could spawn a bubble of true vacuum, expanding outward at the speed of light. Within that bubble, the fundamental constants we take for granted, the strength of gravity, the mass of electrons, might be utterly different, rendering chemistry, biology, and even atomic structure impossible. How real is this threat? The odds are astronomically low, but not zero. Particle accelerators like the Large Hadron Collider have probed energy levels that some theories suggest could trigger vacuum decay, and so far the vacuum has held. But the unsettling truth is that if a decay bubble formed anywhere in the observable universe, we'd have no warning. One moment, everything would be normal. The next, an invisible wall of annihilation would rush toward us at light speed, rewriting physics as it passed. There wouldn't even be time to blink. Yet vacuum decay isn't just a doomsday scenario, it's a window into the fragility of the cosmos. The fact that our universe might exist in a metastable state hints at deeper layers of reality, perhaps even connections to other vacua in a vast multiverse. Some theories suggest that if decay occurred, the new vacuum might generate its own Big Bang, birthing a fresh universe with alien physics. For all its terror, vacuum decay reminds us that the universe is far stranger and far more dynamic than our fleeting human perspective can grasp. And that realization doesn't just reshape how we see reality, it forces us to ask, in a cosmos teetering on the edge of instability, what does it mean to exist at all? Einstein's theory of general relativity has been the cornerstone of cosmology for over a century, a masterpiece that explains everything from the bending of starlight to the warping of time near black holes. But what if it's missing something? A growing chorus of scientists is questioning whether gravity itself might behave differently on cosmic scales, offering an alternative to the mysterious dark energy driving the universe apart. Enter modified gravity theories, bold reimaginings of Einstein's equations that could rewrite our understanding of cosmic expansion without invoking unseen forces. One of the most intriguing candidates is modified Newtonian dynamics. Proposed in the 1980s by physicist Mordechai Milgrom, MND suggests that gravity doesn't weaken as quickly over vast distances as Newton or Einstein predicted. Instead, it tapers off in a way that perfectly mimics the effects of dark matter on galaxy rotations. Imagine driving a car where the gas pedal responds differently depending on speed. Press lightly, and it behaves normally. Press harder, and the engine adjusts to keep acceleration steady. That's the essence of MND, a subtle tweak to gravity's rules that could explain why galaxies spin faster than expected without needing invisible matter. But can modified gravity handle the universe's accelerating expansion? Some versions, like TVS tensor vector scalar gravity, attempt to extend MND principles to cosmological scales, offering a potential dark energy alternative. These theories introduce extra fields or dimensions that subtly alter how gravity interacts with space-time, creating a repulsive effect akin to dark energy's push. Picture a stretched rubber sheet that mysteriously stiffens as it expands, resisting further stretching on its own. If correct, this could mean the universe's expansion isn't driven by an enigmatic force, but by gravity itself playing by different rules in the cosmic void. The real test lies in the data. Mund excels at explaining galaxy rotations but stumbles when faced with galaxy clusters or the large-scale structure of the universe, where dark matter's presence seems undeniable. Observations of colliding galaxy clusters, like the Bullet Cluster, reveal gravity's pull diverging from visible matter, a smoking gun for dark matter that modified gravity struggles to explain. Meanwhile, the cosmic microwave background's precise patterns align beautifully with dark energy models, leaving modified gravity theories scrambling to match their precision. Yet the debate is far from settled. Some researchers argue that dark energy and dark matter are placeholder explanations, a cosmic we don't know yet, disguised as particles and fields. Others point to anomalies like galaxies mysteriously devoid of dark matter or unexpected gravitational lensing patterns as cracks in the standard model's foundation. Truth might lie somewhere in between. Perhaps gravity does behave unusually on certain scales, but still requires some unseen component to fill the gaps. What's at stake isn't just a technical disagreement, it's a fundamental question about how we explore the unknown. Do we invent new substances to preserve our theories, or do we dare rewrite the rules themselves? For now, the universe keeps its secrets close, leaving us to wonder whether dark energy is the final answer or just a clue pointing towards something even stranger. One thing's certain, every time we think we've got gravity figured out, the cosmos finds a way to surprise us. The Ecporotic universe paints a picture of cosmic rebirth unlike anything in traditional Big Bang cosmology. Instead of a fiery singularity bursting into existence, this theory imagines our universe as a three-dimensional membrane, or brane floating in higher dimensional space, occasionally colliding with a neighboring brane like two sheets of paper smacking together in the wind. Each collision isn't destruction but creation. The energy of impact ignites a new cycle of expansion, filling our universe with matter and radiation without the need for an infinitely dense starting point. It's a gentler genesis, one that sidesteps the Big Bang's mathematical headaches while still explaining the universe we see today. What sets this apart from the Big Bang? For starters, the Ecporotic model doesn't rely on inflation to solve the horizon problem, the puzzle of why distant regions of space look so similar. In standard cosmology, inflation stretched the universe faster than light, smoothing out irregularities. But here, the slow, pre-collision approach of the branes naturally stretches and flattens them, like rolling out dough before baking. By the time they collide, they're perfectly uniform, explaining the cosmic microwave background's eerie consistency without requiring a breakneck expansion spurt. Yet challenges remain. Critics point out that brane collisions would generate universe-scorching heat, potentially erasing any traces of previous cycles. How could galaxies, stars, or even the delicate patterns in the cosmic microwave background survive such violence? Proponents counter that quantum effects or hidden dimensions might soften the blow, preserving subtle fingerprints of past eras. Another hurdle is dimensionality itself. We have no direct evidence of higher dimensional space, though theories like string theory suggest it's mathematically plausible. The most tantalizing aspect, the Ecporotic universe might leave detectable echoes. If branes collided at a slight angle, the interaction could create gravitational waves with a distinct signature, faint ripples in spacetime that future observatories might catch. It's a long shot, but the payoff would be staggering, proof that our universe is just one act in an endless cosmic play, with collisions in the dark between dimensions setting the stage for every new beginning. Whether this theory holds up or not, it reminds us that the universe's story might be far larger and stranger than we ever imagined. Black holes aren't just cosmic vacuum cleaners, they might be cosmic wombs. While we typically think of black holes as regions where gravity is so powerful even light can't escape, some theories suggest they could also be portals to entirely new universes. Imagine falling into a black hole, past the event horizon where the laws of physics as we know them break down, only to find yourself not crushed into oblivion, but reborn into a fresh cosmos, its expansion fueled by the black hole's own violent collapse. This isn't science fiction, it's a radical hypothesis that challenges our most basic assumptions about space, time, and the origins of everything. The idea builds on a startling property of black holes: their interiors don't behave like the space outside. While we perceive a black hole as a bottomless pit, the math suggests something stranger. Once you cross the event horizon, space and time swap roles. Falling toward the singularity isn't just moving through space, it's moving forward in time toward an inevitable fate. But what if that singularity isn't the end? Loop quantum gravity, for instance, proposes that black holes might not form true singularities at all. Instead, their crushing gravity could trigger a quantum bounce, rebounding outward as a new universe. Picture a collapsing star not imploding into nothingness, but rebounding like a compressed spring, its energy birthing an entirely new space-time. This isn't just a wild guess, it could solve real cosmic puzzles. For one, it offers an alternative explanation for dark energy's mysterious push. If our universe is expanding within a black hole embedded in a larger, parent universe, the energy of that black hole's formation might still be echoing through our space, stretching it outward. It's like standing in the shockwave of an ancient explosion, still propelling everything away from the center. Even the Big Bang itself might look different in this context. Instead of an explosion from nothing, it could be the rebound of a black hole's collapse, its energy recycled into the birth of our cosmos. Some versions of the theory go even further. If black holes create universes, then every black hole in our cosmos, every stellar remnant, every supermassive giant lurking in galactic centers, could be a doorway to another reality, each with its own physics and history. Our universe might be just one link in an infinite chain, a cosmic matryoshka doll where black holes nest new worlds inside them. This could even explain why the constants of nature in our universe seem so finely tuned for life, because only in universes where black holes can form would new universes arise, creating a selection bias for conditions that allow their existence. Yet for all its elegance, black hole cosmology faces serious challenges. How could a newborn universe inherit its physics from a black hole? Wouldn't the extreme conditions at the singularity erase any trace of structure? And if universes are constantly budding inside black holes, why don't we see evidence of their gravitational influence in our own cosmos? These questions remain open, but researchers keep probing. Some look for subtle imprints in the cosmic microwave background anomalies that might hint at our universe's parent black hole. Others explore the quantum behavior of singularities, searching for clues about how a bounce might unfold. Whether black holes are cosmic creators or not, the idea forces us to rethink the boundaries of reality. If true, it means every black hole is more than a grave for stars. It's a potential genesis, a hidden engine of cosmic renewal. And that transforms the night sky from a static tapestry into something alive with possibility, where even the darkest voids might cradle universes beyond our wildest imagination. The simulation hypothesis flips reality on its head. What if the cosmic expansion we measure, the galaxies we observe, even our own thoughts are nothing more than lines of code in an unfathomably advanced simulation? This isn't just sci-fi speculation. Prominent thinkers like Nick Bostrom and tech visionaries like Elon Musk have seriously entertained the idea that the universe might be a digital construct. If true, it would mean the laws of physics, gravity, the speed of light, even dark energy's relentless push aren't fundamental truths, but programmed parameters like the rules of a video game. But here's where it gets cosmic. If we're in a simulation, is the universe's expansion a deliberate feature or an emergent glitch in the system? Imagine a universe where the Big Bang wasn't a physical event, but the moment the simulation booted up. Dark energy's acceleration could be as simple as a background process running in the cosmic code, allocating more memory to the virtual space between galaxies. Even quantum fluctuations, those tiny, random blips that seeded galaxies, might just be procedural noise, the equivalent of a random number generator ensuring the simulation doesn't look too predictable. Some theorists take this further, suggesting that the Planck length, the smallest possible unit of space, could be the pixel size of our reality, with expansion representing the simulation's resolution increasing over time. Critics, though, argue this is less science than metaphysics. How could we ever test whether we're in a simulation? Some propose looking for compression artifacts, in reality, mathematical patterns or inconsistencies in physical constants that hint at underlying code. Others suggest high-energy particle collisions might reveal the limits of the simulation's processing power, like a computer struggling to render complex graphics. Yet, even if the hypothesis can't be proven, it forces profound questions. If the cosmos is a simulation, who or what is running it? Are we accidental byproducts, or is our curiosity about the universe's expansion part of the experiment? Philosophically, the simulation hypothesis blurs the line between creator and creation. If our universe is designed, does that make dark energy a deliberate mechanism to prevent virtual civilizations from colliding? Or is it a bug, a runaway variable its programmers didn't anticipate? The unsettling beauty of this idea isn't just that it redefines reality. It challenges us to ask whether the universe's deepest mysteries are puzzles to solve, or just the way the simulation was always meant to unfold. And that leaves us with one haunting thought. If we are living in someone else's code, what does that make the coders, gods, scientists, or something we can't even comprehend? Neutrinos are cosmic ghosts, particles so elusive they pass through entire planets like they aren't even there. Born in the hearts of stars, supernova, and even the Big Bang itself, these tiny travelers were long thought to be weightless, slipping through the universe without leaving a gravitational footprint. But in the late 1990s, scientists discovered something startling. Neutrinos do have mass. Not much. A single neutrino is billions of times lighter than an electron. But when you consider how many flood the cosmos, their collective influence could be quietly shaping the fate of everything. Picture this: trillions of neutrinos stream through your body every second, leftovers from the sun's nuclear furnace and distant stellar explosions. They barely interact with matter, but their sheer numbers mean their gravity adds up. Over billions of years, even these whisper-light particles could subtly tug on galaxies, altering how they clump together. Some theories suggest neutrinos might explain why the universe's large-scale structure looks the way it does, why galaxies cluster into vast filaments and walls with enormous voids in between. Like cosmic breadcrumbs, their gravitational trails could have guided the formation of the cosmic web itself, but neutrinos aren't just passive players. Their unique properties create a push-pull dynamic with dark matter, the invisible scaffolding of the universe. Dark matter's gravity pulls matter together, while neutrinos moving at near light speed act like a cosmic wind, smoothing out dense regions and suppressing the growth of smaller galaxies. It's as if the universe has two competing sculptors, one carving deep valleys with dark matter's gravity, the other gently sanding the edges with neutrino streams. This delicate dance might explain why we see fewer dwarf galaxies than simulations predict. Neutrinos could be scattering their formation like seeds in the wind. The stakes are higher than just galaxy counts. If neutrinos skew the distribution of matter, they could also affect how we measure dark energy's acceleration of the universe. Even a slight miscalculation in their influence might throw off our cosmic yardsticks, like supernova brightness or galaxy clustering. That's why scientists are racing to pin down neutrino mass more precisely. Experiments like the upcoming Deep Underground Neutrino Experiment aim to measure these particles with unprecedented precision, while telescopes map the cosmic web for hints of their gravitational fingerprints. What's fascinating is how such tiny particles could hold clues to the universe's biggest mysteries. If neutrinos are heavier than we think, they might tip the scales toward a future big crunch. If lighter, dark energy's expansion could win out unchallenged, either way, these spectral particles remind us that even the faintest voices in the cosmos can shape its grandest structures. And that means the key to understanding the universe's fate might be hiding in the whisper of a neutrino's flight. The next decade of cosmological discovery will rewrite our understanding of the universe's expansion in ways we can barely imagine. At the forefront stands the James Webb Space Telescope, already peering deeper into the infrared universe than any instrument before it. Unlike Hubble, which showed us young galaxies, Webb reveals their embryonic forms, clusters of stars so ancient their light has been stretched into infrared whispers by the universe's relentless expansion. These observations could settle one of cosmology's fiercest debates, whether dark energy's strength has changed over time. If early galaxies clustered differently than predicted, it might hint that dark energy isn't a constant force but something evolving, a revelation that would upend our most fundamental models. Meanwhile, gravitational wave astronomy is entering its golden age. The next generation of detectors, like the Laser Interferometer Space Antenna LISA, will sense ripples in spacetime from collisions so massive they distort the cosmos itself. Imagine detecting the merger of supermassive black holes billions of years ago. Their gravitational waves could carry imprints of the universe's expansion rate at different epochs, creating a cosmic speedometer across time. These waves might even reveal hidden dimensions if their signals show anomalies that suggest gravity leaking into other realms. On the ground, colossal projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time (LSST) will map billions of galaxies in unprecedented detail, creating a time-lapse movie of cosmic expansion. By tracking how galaxy clusters warp light over years, we could spot subtle shifts in dark energy's push or uncover new physics at galactic scales. Even more revolutionary are 21-centimeter radio arrays like the Square Kilometer Array, which will map hydrogen gas from the universe's dark ages before stars formed. This could reveal how expansion rates varied in the cosmos's infancy, testing whether inflation truly happened or if another mechanism set the universe in motion. The wild card, quantum sensors, experiments aiming to measure minuscule changes in gravity on subatomic scales, might detect hints of extra dimensions or dark energy's microscopic fingerprints. Picture a lab experiment so sensitive it could sense the universe's expansion in real time, like watching a balloon inflate from the inside. What ties these efforts together is their potential to turn cosmology from a science of inference into one of direct observation. No longer will we rely solely on abstract equations or indirect clues. We'll watch cosmic history unfold in data streams, hearing the universe's heartbeat through gravitational waves, seeing its wrinkles in ancient light, and touching its hidden fabric with quantum precision. The next era won't just answer old questions, it will reveal mysteries we haven't even thought to ask yet. And that's the real magic. Every time we build a better window into the cosmos, the universe shows us how much darker, stranger, and more wondrous it truly is. The phantom energy scenario sounds like something ripped from a cosmic horror story, an unseen force not just expanding the universe but ripping it apart at the seams. Unlike ordinary dark energy, which pushes galaxies apart at a steady pace, phantom energy grows stronger over time, its grip tightening until not even atoms are safe. Imagine a universe where the space between particles stretches so violently that the bonds holding nuclei together snap like overstretched rubber bands. This isn't just theoretical doom-mongering, it's a real, if extreme, possibility rooted in the equations of cosmology. The math behind phantom energy is deceptively simple. Dark energy's behavior is often described by a parameter called W, which defines its pressure-to-density ratio. If W equals -1, we get the cosmological constant Einstein's steady dark energy. But if W dips below -1, dark energy transforms into something far more sinister. Phantom energy's repulsive force doesn't just counteract gravity, it escalates exponentially like a snowball rolling downhill, gathering mass until it becomes an unstoppable avalanche. The result, a big rip where galaxies, stars, planets, and eventually the very fabric of matter are shredded in a final, cataclysmic instant. What's chilling is that this scenario isn't pure speculation. Observations of distant supernova and the cosmic microwave background leave room for W values slightly below -1, just enough to keep phantom energy on the table. Some models even suggest that phantom energy could explain why the universe's expansion appears to be accelerating faster than expected. But the real question isn't just whether phantom energy exists, it's what its existence would mean for time itself. If space stretches infinitely fast, the concept of a future might cease to have any meaning. Causality could break down, with events becoming so isolated that no signals, not even light, could bridge the gaps between them. Critics argue that phantom energy is more mathematical specter than physical reality. Quantum field theory struggles to accommodate such extreme states without producing nonsensical results like negative kinetic energy or infinite densities. Yet the mere possibility forces us to confront how little we truly understand about dark energy's nature. Is it a constant feature of space or something dynamic, capable of evolving into a cosmic executioner? The implications reach beyond doom scenarios. If phantom energy is real, it could hint at undiscovered physics, a sign that our theories of gravity and quantum fields are incomplete. Some researchers propose that extra dimensions or exotic particles might stabilize phantom energy before it triggers a big rip. Others suggest that the universe might find a way to reset before total dissolution, like a phoenix reborn from its own annihilation. Whether phantom energy remains a hypothetical nightmare or becomes an observational reality, its existence would rewrite the rules of existence itself. The universe has survived countless epochs of change, from the fiery birth of stars to the slow fade of black holes. But phantom energy presents something new, not just an end, but an unraveling. And that raises a haunting question: if the cosmos can tear itself apart, what other extremes might be lurking in the equations we've yet to solve? The causal patch universe presents a humbling idea. What if the cosmos we'll ever know is just a tiny bubble in an unfathomably vast ocean, forever cut off from the rest by the relentless speed of light? Imagine standing in a fog so thick you can only see a few feet in any direction. No matter how far you walk, the fog never lifts. Your visible world stays the same size, even as the landscape beyond remains hidden. That's the essence of our cosmic predicament. Due to the universe's expansion accelerating faster than light can traverse it, there's a hard limit to what we can observe, let alone influence. This isn't just a philosophical curiosity, it reshapes how we understand infinity. At the heart of this concept lies the Hubble volume, the sphere around us where galaxies are still close enough that their light has had time to reach Earth since the Big Bang. Everything outside this volume is racing away so quickly that its light will never catch up to us. It's as if the universe has built an invisible fence and we're forever confined to the yard. But here's the twist: if cosmic expansion continues unchecked, distant galaxies won't just fade from view, they'll disappear from our universe's physics altogether. Their gravitational influence, their light, even their information will vanish beyond an unreachable horizon. The cosmos we study today, already 93 billion light-years across, might be the only cosmos we'll ever have access to. How does this square with the idea of an infinite universe? Mathematically, infinity can exist beyond our causal boundary, but operationally it might as well not. Think of it like an endless library where every book you pick up is written in ink that vanishes the moment you look away. You could spend eternity in that library and never read a single complete sentence. Similarly, an infinite universe with a finite observable patch means we're forever gathering fragments of a story we can't finish. Some theories, like eternal inflation, suggest new Hubble volumes are constantly budding into existence, each with its own laws of physics. But these patches are so isolated that comparing them isn't just difficult, it's physically impossible. This raises a profound question. If most of the universe is fundamentally unknowable, does it even matter? Science thrives on testable predictions, but when whole regions of reality lie beyond empirical reach, cosmology bumps against the limits of its own methodology. Some researchers argue this forces a shift in perspective. Instead of chasing an unreachable whole, we should focus on what's causally connected to us, treating our Hubble volume as a self-contained universe in its own right. Others see it as a call to dig deeper into quantum entanglement or higher dimensions, searching for backdoors to the hidden cosmos. Yet the causal patch isn't just a barrier, it's also a time capsule. As the universe expands, future astronomers will see fewer and fewer galaxies, their skies growing darker as the observable universe shrinks. Billions of years from now, civilizations might arise in a night sky devoid of any galaxies but their own, with no clues that a vaster cosmos once existed. That isolation could make today's golden age of cosmology, where we still glimpse the afterglow of the Big Bang and map distant galaxy clusters, a fleeting window in cosmic history. The universe's expansion doesn't just hide its secrets, it's slowly erasing them, leaving us to wonder how much we've already lost to the void. Cosmic strings are like the universe's stretch marks, thin, unimaginably dense threads left over from the violent symmetries of the early cosmos. Picture space-time as a frozen lake, and these strings as cracks in the ice, remnants of a phase transition when the universe cooled from a seething, unified force into the distinct particles and energies we know today. Unlike black holes which crumple space into points, cosmic strings are one-dimensional defects, thinner than a proton but with the mass of a mountain range packed into every inch. Their gravitational pull is so intense they could bend light around them like a twisted funhouse mirror, creating double images of distant galaxies or leaving jagged scars in the cosmic microwave background. But what do these ghostly filaments have to do with cosmic expansion? Some theories suggest they might act as cosmic puppet strings, subtly tugging matter into the vast web of galaxies we observe. In the early universe, their immense gravity could have provided the scaffolding for gas and dark matter to clump around, accelerating the formation of the first stars and galaxies. Even today, a network of these strings, if they exist, might be warping space-time on scales so vast we've yet to detect their fingerprints. Imagine an invisible spiderweb stretching across the cosmos, its threads gently steering the motion of galaxy clusters over billions of years. The real intrigue lies in their potential to solve cosmic mysteries. If dark energy's repulsive force seems too finely tuned, cosmic strings could offer an alternative explanation for why the universe's expansion rate behaves the way it does. Their tension, the energy stored in their stretched fibers, might contribute a bizarre form of negative pressure, mimicking dark energy's effects without requiring new physics. It's like discovering the wind you thought was pushing you forward was actually the pull of invisible ropes all along. Yet detecting these strings is a challenge worthy of a cosmic detective. Unlike black holes or neutron stars, they don't emit light or gravitational waves unless they snap. When a cosmic string vibrates or breaks, it could send ripples through space-time, bursts of high-energy radiation, or even fleeting distortions in the light from distant quasars. Experiments like pulsar timing arrays, which monitor the precise ticks of dead stars for gravitational wave disturbances, might one day catch these echoes. Others search for telltale kinks or cusps in the string's structure that could produce sudden, explosive bursts of energy. The stakes are higher than just adding another oddity to the cosmic zoo. If cosmic strings exist, they'd be a direct window into the universe's first trillionth of a second, a time when all forces were one and space-time itself was a seething quantum foam. Their properties could reveal whether grand unified theories' attempts to marry quantum mechanics with gravity are on the right track. And if they're tangled into loops, these strings might even have birthed the seeds of supermassive black holes, linking the universe's largest structures to its smallest defects. For now, cosmic strings remain tantalizing what-ifs, their existence hovering between mathematical elegance and observational elusiveness. But whether they're out there or not, they force us to reckon with a profound truth. The universe's grandest structures might be built on flaws we've yet to see, cracks in reality that shaped everything from the first stars to the fate of expansion itself. And that's the real magic of cosmology. It's not just about what we observe, but about the invisible threads that might be weaving the story all along. Black holes aren't just cosmic vacuum cleaners, they're shredders, tearing apart the very fabric of information itself. When a star collapses into a black hole, it doesn't just vanish, it leaves behind a gravitational fingerprint, a mass, a spin, an electric charge. But what happens to the rest, the star's composition, its history, even the atoms that once made up planets orbiting it? All of it seemingly disappears behind the event horizon, lost to the singularity. This is the heart of the information paradox, a puzzle so deep it challenges our understanding of reality's most fundamental laws. At first glance, the paradox seems straightforward. Quantum mechanics insists information can never be destroyed. It might change form, but it's always preserved, like rearranging the letters in a book rather than burning it. Yet general relativity paints a bleaker picture. Anything crossing a black hole's event horizon is gone for good, crushed into oblivion. Stephen Hawking's groundbreaking work in the 1970s only deepened the mystery. He showed that black holes aren't truly black, they emit radiation, slowly evaporating over eons. But here's the catch, that radiation appears random, carrying no trace of the information swallowed by the black hole. It's as if a library burned down, leaving behind only ashes with no way to reconstruct the books. The stakes couldn't be higher. If information truly vanishes, it undermines quantum theory, the framework governing everything from atoms to superconductors. Physicists have proposed wild solutions to this conundrum. One idea is holography, the notion that all the information falling into a black hole isn't lost but smeared across its event horizon like a cosmic hard drive. Picture a two-dimensional surface encoding the details of a three-dimensional object, like a DVD storing an entire movie. In this view, the singularity isn't a pit of destruction but a transformation, scrambling information into a form we don't yet understand. Another radical proposal is the firewall hypothesis. Imagine the event horizon not as a silent boundary, but a raging inferno of high-energy particles, a wall of fire that incinerates anything crossing it. This would preserve information by ensuring it's never truly inside the black hole, but it violates Einstein's principle that free-falling observers should notice nothing unusual at the horizon. It's like claiming the edge of a waterfall is suddenly a sheet of lava, a solution that creates as many questions as it answers. Then there's the possibility of baby universes. Some theories suggest that black holes might spawn entirely new cosmos inside them, with the parent black hole's information woven into the fabric of the newborn universe's laws. It's a poetic idea, black holes as cosmic wombs rather than graves, but it's nearly impossible to test. How would we ever peer into another universe to check? The paradox isn't just about black holes, it's a microcosm of the tension between quantum mechanics and gravity, the two pillars of modern physics that refuse to fit together neatly. Solving it might require rewriting the rules of one or both, revealing a deeper theory that unifies them, and that's where cosmic expansion adds another layer of intrigue. If the universe's accelerating expansion leads to a heat death, a state of maximum entropy where no new information can be created, does that mean all information will eventually become inaccessible, lost in a cold, featureless void? Or does it too endure in some form we can't yet imagine? What makes this puzzle so captivating isn't just the physics, it's the philosophy. Information isn't just data, it's the universe's memory, the record of everything that's ever happened. If it can truly disappear, what does that say about the nature of reality? And if it's preserved, where and how does it hide? The answers might lie in the uncharted territory where quantum weirdness meets gravitational might, a frontier that could redefine not just black holes but existence itself. The Boltzmann brane paradox is one of the strangest, most unsettling thought experiments in all of physics, a cosmic riddle that makes you question not just the nature of reality, but whether your own thoughts can be trusted. Here's the chilling premise. In an eternally expanding universe where entropy marches toward maximum disorder, random quantum fluctuations could, given enough time, spontaneously assemble a fully formed, self-aware brain out of the chaos. Not attached to a body, not born from evolution, but a lone, conscious mind popping into existence, complete with false memories of a life it never lived. And statistically, in an infinite cosmos, these phantom minds should outnumber real, biologically formed brains by an unimaginable margin. So why aren't we all Boltzmann brains? The paradox takes its name from Ludwig Boltzmann, the 19th century physicist who revolutionized our understanding of entropy. He realized that even in a universe trending toward disorder, tiny pockets of order can emerge purely by chance, like a gust of wind randomly assembling a sandcastle from scattered grains. Fast forward to modern cosmology, and the implications become mind-bending. If the universe truly lasts forever, as some dark energy models suggest, then even the most improbable events become inevitable. Given enough time, particles jostling in the void could arrange themselves into a functioning brain, complete with fabricated sensory input convincing it that it's a person standing on a planet watching the stars. This isn't just a quirky hypothetical, it's a direct challenge to how we interpret probability and observation. If Boltzmann brains are statistically more likely than real observers like us, then our confidence in being genuine products of cosmic evolution collapses. Every memory, every scientific measurement, even the certainty that the universe is 8 billion years old could be an illusion generated by a fluctuation. It's the ultimate solipsistic nightmare, the suspicion that you're not just a brain in a vat, but a temporary accident of quantum noise, destined to dissolve back into the void as quickly as you appeared. Critics counter that the paradox reveals flaws in our assumptions, not reality. Maybe the universe isn't infinite, or dark energy's expansion won't last forever. Others argue that consciousness can't emerge from random fluctuations, that it requires the precise, sustained complexity of biological evolution. But the most compelling escape route comes from quantum field theory. True vacuum states, the most stable configurations of reality, might not allow Boltzmann brains to form at all. Like trying to balance a pencil on its tip indefinitely, any fluctuation complex enough to create consciousness would instantly unravel under the weight of entropy. The paradox forces us to confront the uneasy intersection of cosmology and philosophy. If we dismiss Boltzmann brains as absurd, we might be clinging to intuition over math. If we accept them, science itself becomes untrustworthy, a hall of mirrors built by imaginary observers. Either way, the universe is telling us something profound, that infinity and probability can conspire to create realities far stranger than fiction, and that our place in the cosmos might be even more precarious or miraculous than we ever imagined. Quantum entanglement is often described as spooky action at a distance, a phenomenon where two particles become so deeply linked that measuring one instantly influences the other, no matter how far apart they are. This bizarre connection defies classical physics, and yet it's been proven in labs time and again. But what if this quantum weirdness isn't confined to tiny particles? What if entanglement stretches across the cosmos itself, weaving invisible threads between galaxies and shaping the universe's expansion? At first glance, the idea seems outlandish. Entanglement is fragile, easily disrupted by interactions with the environment. How could such delicate connections survive the violent chaos of the early universe? Yet some theorists propose that entanglement might have left its mark on the large-scale structure we see today. Picture the infant cosmos, a seething plasma of particles, so dense and hot that every interaction was a quantum event. In that primordial soup, entanglement could have been ubiquitous, linking regions of space that later expanded far beyond each other's horizons. These ghostly bonds might have guided how matter clumped together, leaving faint imprints in the distribution of galaxies. The real smoking gun could lie in the cosmic microwave background, the afterglow of the Big Bang. If entanglement played a role in the universe's earliest moments, it might have created subtle patterns in this ancient light, correlations between points that should have never been in causal contact. Some models even suggest that the uniformity of the CMB, the fact that distant regions look eerily similar, could owe something to quantum entanglement acting as a cosmic synchronizer, linking patches of space before inflation blew them apart. But how could entanglement influence expansion itself? One radical idea involves dark energy. If empty space isn't truly empty, but a quantum froth of entangled particles constantly flickering in and out of existence, their collective energy might contribute to the repulsive force driving galaxies apart. It's as if the universe is held together by an invisible web of quantum connections, and the tension in that web is subtly stretching space itself. Another possibility ties entanglement to black holes. When matter falls into a black hole, its information gets scrambled onto the event horizon, a process that might create new entangled states, releasing energy that could fuel cosmic expansion in ways we don't yet understand. Skeptics point out the staggering scale problem. Entanglement works wonders for electrons in a lab, but extrapolating it to galactic distances requires physics we haven't discovered yet. Others argue that entanglement's effects would be too weak to compete with gravity or dark energy on cosmic scales, yet the math holds tantalizing possibilities. If space-time itself emerges from quantum entanglement, an idea gaining traction in holographic principle theories, then the expansion of the universe might not be about stretching space, but about the evolution of these underlying quantum links. Whether entanglement shapes the cosmos or not, the question itself reveals how deeply quantum mechanics might be woven into the fabric of reality. The universe began as a quantum object, and even as it grew to astronomical sizes, those quantum roots might still be holding sway, invisible but undeniable. And that's the real magic of this idea. It forces us to see the cosmos not just as a collection of galaxies and forces, but as a quantum system on the grandest possible scale, where the spooky connections of the very small might still be pulling the strings of the very large. The holographic inflation model merges two of cosmology's most mind-bending ideas: inflation's explosive growth and the holographic principle's radical reduction of reality into a single, elegant framework. Picture the early universe not as a three-dimensional volume expanding into nothingness, but as a two-dimensional surface vibrating with quantum information. its rapid growth projected like a cosmic hologram into the space we perceive. This isn't just poetic imagery, it's a mathematical dance where the universe's earliest moments are encoded on a boundary we can't see, solving puzzles that have stumped physicists for decades. Take the horizon problem, the mystery of why distant regions of the cosmos look so similar despite never having been in contact. Standard inflation solves this by stretching space faster than light, smoothing out irregularities. But the holographic inflation model offers a sleeker explanation. If the universe was always described by a lower dimensional boundary, those regions weren't truly separate to begin with. They were linked like pixels on a screen, part of the same underlying code. The uniformity isn't a coincidence, it's baked into the hologram structure. Then there's the question of quantum fluctuations, those tiny ripples that seeded galaxies. In traditional inflation, these arise randomly from quantum noise. But holographic inflation suggests they're not random at all. They're shadows of entangled quantum bits on the boundary, their patterns woven into the fabric of space-time like a hidden message in a tapestry. Imagine shaking a sheet of paper and watching the vibrations form intricate patterns, except the paper is the edge of reality, and the vibrations become galaxies. Mathematically, the model is a breathtaking synthesis. It treats gravity not as a force acting within space, but as an emergent property of information flow between dimensions. The equations reveal a startling trade-off. The more the universe expands in 3 dimensions, the more densely packed information becomes on its 2-dimensional boundary. It's as if the cosmos is a growing crystal, its structure dictated by the intricate arrangements of atoms at its surface. Critics argue the model is untested, relying on abstract math rather than observable predictions. Yet its proponents point to subtle signatures, specific patterns in the cosmic microwave background or gravitational waves, that might one day reveal the universe's holographic origins. And if they're right, it would mean our reality isn't just expanding, it's unfolding, layer by layer, from a hidden surface where all the answers are already written. The holographic inflation model doesn't just solve cosmic puzzles, it redefines what it means for the universe to exist at all. The early universe wasn't just a hot, dense soup of particles. It was a bubbling cauldron of symmetry breaking, where fundamental forces split apart like ice forming cracks in a freezing lake. These cosmic phase transitions didn't just create the physics we know today. They might have left behind scars in the fabric of reality itself, topological defects. Picture these defects as cosmic knots, twists in space-time so stubborn they can't smooth themselves out, remnants of a time when the universe was still figuring out its own rules. Among these theoretical oddities are domain walls, sheet-like barriers separating regions of space with different quantum properties, cosmic strings, one-dimensional cracks in space-time, and magnetic monopoles, solitary particles with a single magnetic pole that defy everything we know about magnets. But the most tantalizing question isn't just what these defects are, it's whether they've been silently shaping the universe's expansion all along. Take cosmic strings first. These infinitesimally thin but unimaginably dense filaments could stretch across the entire cosmos, carrying the gravitational weight of entire mountain ranges packed into every inch. Their presence would warp space-time around them, bending light like a funhouse mirror and potentially seeding the formation of galaxies by pulling matter into their gravitational wake. Some theories even suggest strings could explain mysterious patterns in the cosmic microwave background, those faint whispers of the Big Bang where their sharp gravitational signatures might have left faint, jagged imprints. But here's the twist: if strings exist, their tension, the energy stored in their stretched fibers, could act like a cosmic drumhead, vibrating over eons and emitting gravitational waves we might detect with future observatories. Imagine hearing the echoes of defects born in the universe's first trillionth of a second, long before atoms or even light existed. Then there are domain walls, vast membranes dividing the cosmos into distinct regions where the laws of physics might subtly differ. These walls would be like cosmic fault lines, with space itself shifting abruptly as you cross from one side to the other. In the early universe, their gravitational pull could have accelerated the clumping of matter, sculpting the large-scale structure we see today. But there's a catch. If domain walls were too common, their collective gravity would have overwhelmed the universe long ago, warping expansion in ways we don't observe. That's why most models suggest they're rare or already decayed, leaving only faint traces for us to hunt. Magnetic monopoles, on the other hand, are cosmic unicorns, particles with a north pole but no south, or vice versa. Their existence was predicted by grand unified theories, which suggest that in the universe's infancy, electromagnetism and the nuclear forces were one and the same. When these forces split, monopoles should have formed in abundance, so many, in fact, that their sheer mass would have slowed cosmic expansion to a crawl. But we don't see them. This monopole problem was one of the key puzzles that led physicists to propose cosmic inflation, a period of hyper-fast expansion that would have diluted monopoles to near nothingness. Yet some theorists wonder if a handful survived, lurking in the cosmic shadows. If we ever found one, it wouldn't just rewrite textbooks, it'd be a smoking gun for the universe's first moments. But what if these defects aren't just relics? Some wilder models propose they could be active players in cosmic expansion. Certain types of domain walls, for instance, might exert negative pressure, a repulsive effect mimicking dark energy's push. Cosmic strings, if they formed loops, could collapse into black holes, seeding the supermassive giants we now find at galactic centers, and monopoles. If they clustered in hidden regions, their gravity might subtly skew the motion of galaxies in ways we've yet to detect. The challenge is that topological defects exist at the intersection of particle physics and cosmology, requiring insights from both to pin them down. Experiments like the Laser Interferometer Gravitational Wave Observatory LIGO could one day catch the ripples from colliding strings, while deep space telescopes might spot the telltale shadows of domain walls warping distant starlight. Whether these defects are cosmic fossils or hidden architects, their study forces us to confront how much we still don't know about the universe's scaffolding. They remind us that the cosmos wasn't just born, it was forged in a series of violent transitions, each potentially leaving behind clues we're only beginning to decipher. And that's the real magic. Somewhere between the math and the mysteries, topological defects could be the missing link in understanding why the universe looks and expands the way it does. The arrow of time feels as undeniable as gravity. We remember the past, not the future. Shattered glass never reassembles itself. The universe grows ever more disordered. But what if time's relentless forward march isn't fundamental? What if it's just a side effect of cosmic expansion, a fleeting phenomenon that could vanish if the universe stops growing or collapses? This isn't science fiction, it's a possibility rooted in the deep connection between time's flow and the universe's accelerating stretch. At the heart of this idea lies entropy, the measure of disorder that gives time its direction. From the moment of the Big Bang, the universe has been racing toward higher entropy, like a clock winding down. But entropy's rise depends on space itself expanding, creating room for new configurations of matter and energy. Think of it like shuffling a deck of cards. The more space between the cards, the more ways they can be arranged. If expansion were to halt, entropy might max out, leaving no meaningful way to distinguish past from future. Time wouldn't just slow, it could stop altogether, freezing reality in an unchanging snapshot. Now imagine the opposite scenario, a big crunch. As the universe contracts, space tightens, squeezing matter and energy into an ever smaller volume. Entropy wouldn't just plateau, it might reverse, erasing time's arrow as neatly as rewinding a film. Particles would retrace their steps, galaxies would reassemble, and the cosmos would march backward toward order. But here's the twist. Physics doesn't care whether time runs forward or backward. The equations work either way. What we perceive as time's direction might just be a quirk of living in an expanding universe, like fish assuming water flows only downhill because they've never seen the ocean's tides. The stakes get even stranger when you consider black holes. Near a singularity, gravity warps space-time so severely that time and space swap roles. Falling toward the singularity isn't just moving through space, it's moving toward an inevitable moment in time. If the universe collapses into a singularity, could time itself unravel, becoming just another dimension crushed into oblivion? Some models suggest that in a cyclic universe, each new Big Bang resets time's arrow, meaning our cosmic moment is just one tick in an endless clock with no master timeline. Then there's dark energy's role. If it accelerates expansion forever, the universe might reach a state where space stretches so fast that cause and effect break down. Events become isolated, unable to influence one another, rendering time meaningless. No clocks could tick, no memories could form, just an eternal, featureless void where before and after lose all meaning. The chilling beauty of these theories isn't just their audacity, it's how they reframe our place in the cosmos. Time, the scaffold of human experience, might be nothing more than a local phenomenon, as fleeting as a bubble in boiling water. Whether it ends with a crunch, a freeze, or a fade, one thing's certain. The universe's expansion isn't just shaping space, it's writing the very rules of time itself. And that leaves us with a haunting question. If time can vanish, was it ever truly there to begin with? From the searing dawn of the Big Bang to the speculative echoes of a big crunch, the universe's breath, its expansion and contraction remains one of science's most captivating enigmas. We've traversed landscapes where dark energy stretches the cosmos like taffy, where quantum fluctuations birthed galaxies from nothingness, and where brains collide in hidden dimensions to spark new cycles of existence. Each theory, from cosmic inflation to holographic universes, isn't just a mathematical abstraction. It's a story about where we came from and where we're headed. The universe might unravel in a big rip, its very atoms torn apart by phantom energy, or it could collapse inward, resetting the cosmic clock in a fiery rebirth. Or perhaps it will fade into silence, a heat death where time itself loses all meaning. What's astonishing isn't just the diversity of these visions, it's how they reveal the audacity of human curiosity. Centuries ago, we mapped stars. Today, we map the fabric of space-time, chasing clues in the afterglow of the Big Bang and the whispers of quantum foam. The theories we've explored are more than scientific hypotheses. They're mirrors reflecting our deepest questions about existence. Are we alone in the cosmos, or is every black hole a portal to another reality? Is the universe a singular masterpiece, or one page in an infinite library of multiverses? The beauty of these mysteries is that they're not static. Every new telescope, every gravitational wave detection, every lab experiment probing quantum gravity could rewrite the narrative. The James Webb Space Telescope might uncover galaxies too ancient for conventional cosmology. Future gravitational wave observatories could catch echoes of colliding branes or cosmic strings. Even now, lurking in data or scribbled on a theorist's chalkboard might be the next revolution, an idea that reshapes our understanding of everything. So as we reach the end of this cosmic journey, let's not think of it as a conclusion but as an invitation. The universe's story is still being written, and each of us gets to be part of it. Whether you're drawn to the elegance of string theory, the brutality of vacuum decay, or the poetry of a cyclic cosmos, your wonder fuels the next chapter. Drop your favorite theory in the comments. Is it the holographic principle, the multiverse, something wilder? And let's keep the conversation spinning like a pulsar. Don't forget to subscribe for more deep dives into the universe's grandest puzzles. The cosmos isn't just out there, it's unfolding all around us, waiting for those bold enough to look. Until next time, keep your eyes on the skies and your mind open to the impossible. After all, the greatest discoveries often begin with a simple question: what if?